Welcome back, everyone. Today we are diving into an absolute marvel of modern mega engineering. We're going to look at exactly how humans take apart a massive mountain of solid rock from the inside out. And we do this using a highly productive, hyper-efficient method called sublevel stoping. So if you've ever wondered how the raw materials for our cities, our cars, and all our tech are pulled from deep within the earth, well, you're absolutely in the right place. Let's get started. Here's our roadmap for this explainer. First, we'll cover the anatomy of stoping. Then we'll walk through the sequence step by step, starting with mine development, creating the slot raise, long hole drilling, charging and blasting, and finally, mucking and extraction. Section 1. The anatomy of sublevel stoping. Okay, let's dive into this. To really wrap your head around this method, I want you to imagine building a skyscraper, but in reverse, and deep underground. We use this specific method for ore bodies that are steeply dipping, which means they plunge downwards at angles greater than 60 degrees, and they also have to be highly competent. Competent just means the rock is incredibly strong and stable. Instead of fighting gravity to haul broken rock up level by level, we start from the bottom and let gravity do all the heavy lifting for us. We literally slice the massive vertical ore body into distinct horizontal layers called sublevels. So we're essentially creating this highly organized vertical factory. Miners work from these horizontal sublevels, drilling long holes into the ore block between them, and systematically prepping the entire column for extraction. Now, before we go any further, we really need to define the word stope. A stope is simply the large, open void created inside the earth after the rock is blasted and the ore is extracted. And I really want you to grasp the massive scale here. We're not talking about little caves. These are cavernous, cathedral-sized empty spaces that we are systematically creating deep underground. And way down at the very bottom of that massive stope, we have the drawpoint. You can think of this kind of like the spout of a giant funnel. Because we're relying so heavily on gravity, all those hundreds of thousands of tons of blasted rock from the stope above are eventually going to tumble down to this exact extraction point for collection. So this all builds into a structured 5-step sequence backbone that we are going to strictly follow today. It starts with development, moves to the slot raise, then long hole drilling, charging and blasting, and finishes up with mucking. Step 1. Mine development. Before a single ounce of profitable ore is ever blasted, the initial physical pathways have to be painstakingly carved out of solid, unforgiving rock. And let me tell you, this is an immense upfront effort. You need main access ramps spiraling down into the earth, level drives, ore drives, and of course, ventilation raises just to keep the air breathable. But most importantly, you need to excavate those horizontal sublevels we discussed a minute ago. These are typically spaced anywhere from 20 to 40 meters apart vertically. Now, here's the big trade-off. Putting these sublevels closer together actually improves your drilling accuracy later on, but it massively drives up your upfront development costs. Step 2. Creating the slot raise. Okay, so once our whole network of tunnels is established, we move to what is arguably the most crucial prep work for the entire mining sequence. You see, you can't just detonate a solid block of rock if the energy and the expanding rock have nowhere to go. If you try, well, it's just going to turn into packed dust right there in place. So miners use specialized methods, like raise boring or long hole raise blasting, to drill a vertical shaft. We call this a free face, and it goes right through the ore block. This empty vertical column gives the rest of the rock room to expand and break apart effectively when the main blast actually happens. Step 3. Long hole drilling. Now, what's really interesting about this is how, with that freeze face established, we transition into primary production. The mountain is being meticulously prepped for destruction. Miners use top hammer and in the hole, or ITH, drilling equipment to punch these massive ring patterns of holes straight into the ore from the sublevels we built earlier. They'll drill upward toward the level above and downward toward the level below. This creates this incredible 3D web of incredibly precise boreholes. Deep in the drifts, you'll find these Simba long-hole drilling rigs maneuvering in super tight spaces. They're drilling perfectly aligned holes that range from 2 inches all the way up to a massive 8.5 inches in diameter. And I cannot stress enough how vital precision is here. If these holes drift off target by even a fraction of a degree over a 30-meter length, your entire blast is going to be severely compromised. Step 4. Blasting the rock. So that extreme precision leads us directly to the release of all this built-up kinetic energy. Those long holes are pumped full of explosives and then detonated in these carefully timed microsecond sequences. The solid rock violently fragments, it expands right into that slot raise we built earlier, and then the entire face just collapses into the open stope. And, one of the absolutely greatest advantages of sublevel stoping is safety. Because this entire process is heavily mechanized and designed to be done remotely, workers remain completely out of the stope. They are perfectly safe inside the supported access tunnels during the actual blast. And this brilliantly illustrates the real payoff of our reverse skyscraper strategy. We get to watch gravity go to work. The blasted, fragmented ore goes into a free fall through the massive stope void we just created. It tumbles all the way down, funneling neatly through a conical ore pass straight down to the haulage drift below. Step 5. Extracting the ore, also known as mucking. All of that tumbling rock lands perfectly in place for our final stage. Now we settle into the highly rhythmic mechanical process of mucking, which is just the mining term for scooping up the prize. To handle this, we bring in the big guns, load haul dump machines, or LHDs. These are incredibly low-profile, heavily armored workhorses specifically designed for subterranean extraction. They drive right up to those drawpoints we defined earlier, right where the mountain of fragmented ore is piled up. During the mucking process, the loader aggressively scoops up the broken rock from the drawpoint, backs out, and hauls that payload through the lower transport drift. Then it either dumps the ore into deeper internal ore passes or straight into massive underground haul trucks. From there, it's transported completely out of the mine and up to the surface for processing. This constant rhythmic cycle of mucking is what actually drives the profitability of the mine. Generally speaking, sublevel stoping achieves a fantastic 80 to 90% ore recovery rate. But remember that precision drilling we talked about? If drill accuracy isn't perfectly maintained, or if the walls aren't quite as stable as we initially thought, waste rock from outside the ore body will collapse into the stope. This leads to a 10 to 20% waste rock dilution, and that means these incredibly expensive LHDs are suddenly wasting time and fuel hauling worthless rock to the surface.
The trade-offs, the pros and cons.
Now that we've walked through the entire sequence, all the way from development down to mucking, let's take a step back and quickly evaluate the pros and cons of this massive engineering methodology, because it really is a delicate balance. On the pro side, it's incredibly fast, highly productive, exceptionally safe for the workers, and it has very low operating costs per ton once it's up and running. But on the con side, it requires a ridiculously steep upfront financial investment for all that tunnel development. There's also a constant risk of rock dilution, and most strictly, it completely relies on the surrounding rock being incredibly strong so those massive empty stopes don't just prematurely cave in on themselves. Which really leaves us with this final thought. As the easy-to-reach, shallow deposits of copper, gold, and zinc start to vanish from the Earth's surface, our reliance on the deep underground is only going to grow. Will hyper-efficient, gravity-fed methods like sublevel stoping become our only viable path to sustain the modern world's completely insatiable metal demands? It's a fascinating challenge for the engineers of tomorrow. Thank you so much for joining me on this explainer. Keep asking questions, and I'll see you in the next deep dive.